Yes, hello students, welcome to Unacademy, India's largest learning platform. Myself Sunil Manjani, 15 plus years of teaching experience. Okay, mentored thousands of students for GATE ESE semester exam. I myself cracked ESC, sorry, GATE and ESC exam Mahajan ko Mahadiscom. Okay, Mahadiscom various times during my tenure. Okay, as a student. So let us see the steps involved in steps involved in using Unacademy app. Okay, so let us see what is how to install it. Use Unacademy Learning app. Install it through Google Play Store and App Store. Okay. Go to manage goals. Select Gate and ESC. Then go to plus subscription. Go then select get subscription button. Then go to the subscription type. Okay. So you have got so 12-month package of 27,225 in plus subscription and 24-month package of 39,600 in plus subscription. If you select iconic, you will have to pay 45,225 for 12-month subscription, and the cost for 24 months subscription is 66,600. Okay. So plus subscription will give you India's best educator, interactive live classes, structured courses and PDF live tests and quizzes. Iconic subscription will give you India's best educator, interactive live classes, structured courses and PDF, live tests and quizzes, personal coach, personalized test analysis, study planner, preparatory study material and all that. Okay, preparatory study material and all that. Okay. So let us see MATLAB fundamentals. In this we are going to study in today's session stability analysis using MATLAB. So straight away we will see the example. Okay. Example is find force of transfer function GS is equal to 1.5s plus 1 divided by s cube plus 2s square plus 2.5s plus 0.5. Okay. You have to also determine whether system is stable or not. Also plot poles and zeros of GS in S plane. Okay, you have to determine system stability by simulating impulse response. Okay, so see the what is the program? What is the program okay? So first of all, clear all CLC num equal to, instead of g I will write down simple numerator equal to, see the function 1.5 is s, coefficient 1 is denominator is equal to, see the example, this one coefficient, two coefficient, 2.5, 0.5, so 1, 2, 2.5, 0.5. So I'll write down 1 space 2 space 2.5 space 0.5 like this. Okay. What you need to determine poles. Find the poles of transfer function. To find poles, just a minute. So for poles, denominator, polynomials, denominator polynomial equal to 0 and find its roots. ठीक है, ये रूट्स, ये स्टेटमेंट मैंने लिख लिया है. Okay, so what we'll do, we'll write down the command roots of denominator. This is the command we'll write down. Okay, let us see. Roots denominator. Okay, we'll write down roots denominator. Then what we'll do is, using this we'll find out poles. Okay, whatever the roots will be there, so poles are roots of this transfer function. Okay, transfer function. So I will say r equal to roots. So tell me, after finding our roots, how to calculate roots, how to calculate or display system is stable. See here, if roots are in left side of the S plane, This is right side, left side of the S plane. This is sigma j omega minus j omega. Okay. So this is minus sigma. If roots are in left side of the S plane, if roots are on left hand side of S plane, system is stable. Stable. Okay. Now that means roots are simple also. Simple roots. Okay. Complex conjugate rules. Complex conjugate roots. Okay. What is their common for stability? Their real part of roots. Real part of roots must be negative. Must be negative. Okay. So what I will write down in the program. Okay. So suppose obviously if you see the equation, this is a third order equation, so it will have three roots. So I will say S1 is equal to real part of R. Okay, just a minute. Okay. So R is equals to roots of denominator. So R will have three entries. Entry 1, entry 2, entry 3. Entry 3. Okay. Three entries. So I will say S1 is equal to real part of R of 1. S2 is equal to real part of R of 2. S3 is equal to real part of R of 3. Now I will write down if statement. If S1 and S2 and S3 is is sorry less than, negative means less than 0, not equal to 0 also, less than 0. Okay. If S1 and S2 and S3 is less than 0, display system is stable. Okay. else if else if okay. After these three you can write down imaginary part also. S11 is equal to imaginary of R1. S12 is equal to imaginary of R2. S13 is equal to imaginary of R. See here, roots are negative, system is stable. If roots are 0, okay, roots are 0, the system is any one root is uh, 0, okay, then I will say that that means real part is 0, that is it is on imaginary axis, so system is marginally stable. Marginally stable. Okay, else if S1 or S2 or S3 equal to 0, display system is marginally stable. Bracket close. If again else if S1 or S2 or S3, okay, or S3 is greater than 0, display system is unstable. Even if one root is on right hand side, system is unstable. Okay, and so in this way you can find out the stability of the system. Okay, so for that you don't require any of this imaginary part calculation. Any of this imaginary part calculation. So what I will do is I will omit this part. So this is the program. Okay, S1 less than 0, marginally stable. Okay, system is unstable. So system is table. After that, what you want to do in the program, okay, you need to plot pole zero plot. So pz map is equal to numerator comma denominator. Okay, after that you want impulse response, so simply impulse numerator comma denominator, numerator comma denominator. So this is the impulse response. Okay, so let us see with hands on. Let us see with hands on. I will delete the figure. New script file, clear all, clear all. Okay, TLC numerator is equal to 1.5 space 1, denominator is equal to 1 to 2.5, 0.5. Okay, 1 to 2.5 and 0.5. Okay, then I will say roots is equal to denominator. Okay, or I will say r equal to roots equal to denominator. Let us see, we will save this, and we will save this with stability 1. Let us run this part of the program. So is it okay? That's fine. I will say S1 is equal to real of R1 S2 is equal to real part of R2. S3 is equal to real part of R3. Okay, again save this, then run. Okay, let us see if this is correct. Real. Okay. Save. Okay. Okay. So let us see. I will write down full form REL. Okay. So you can find out the real parts. Okay. Now I will write down. Okay. If S1 the all ports, all real parts of the poles must be equal to, must be at, all roots must be at left hand side of S plane. So S3 in bracket, okay, is less than 0, is less than 0, display system is stable. Okay, else if S1 any imaginary real part is, any real part is 0, it is imaginary table. Okay, S1 and S2 and S3, okay, less than 0 and S1 or S2 or S3 equal to 0. Okay, real parts are equal, imaginary parts are equal, sorry, not imaginary, real parts are equal to 0, I will say. Okay, then display system is marginally stable. System is marginally stable. Else if system is marginally stable. Marginally stable. Okay. So let us see that this is the else if S1 or S2 or S3 or S3 is greater than 0, that means real part is greater than 0, then display system is unstable. Okay. Else displays system is unstable. Okay, then I will put an end to this if statement. Okay, in this way you can determine whether system is stable or not. Then I will say pole 0 map numerator comma denominator, denominator. Okay, what about impulse response? What will be the code? Impulse numerator comma denominator. Okay, let us save this. Hit the enter button. Okay, let us see where is the problem. Column number, here we have got one extra bracket. So syntax error. Okay, it should come system is unstable. S1 and S2 and S. less than 0. Is S1 less than 0, let us see, and S2 less than 0 and S3 less than 0. Okay, the system is unstable. Let us run this program. Now it is okay. In this way, you cannot club together because you have to ask individually. You have to ask individually. So I will say S1 equal to 0, S1 equal to 0, and S2 equal to 0, and S3 and S3 equal to 0. Okay, system is marginally stable. System is marginally stable. Okay. So I will save this. System is stable. Let us now make a change. Let us now make a change to numerator and denominator value. Okay. Let us see that this is only 1. That means 1 upon s plus 1 into s plus 2. So this is denominator is 1 space 2. S plus 1 into s plus 2. Okay. Let us see that what will happen. Okay. If I write down the response of this system, let us see. So if transfer function is equal to 1 upon s plus 1 s plus 2, that means if I say denominator equal to 0, s plus 1 s plus 2 equal to 0, s is equal to minus 1, s is equal to minus 2, minus 1 minus 2. So roots are, what are roots? What is real part? Real part is minus 1 minus 2. You want 0 real part. So s is equal to 0 plus jx if I want a 0 real part. Then this will be equal to s minus jx equal to 0. So let us consider the transfer function. Transfer function is equal to 1 upon s minus j1 s minus j2. Okay. That is equal to 1 upon s square, 1 upon s square minus j2s minus j1s minus minus plus j square 2. Okay, let us see s square minus j3s minus 2. So we cannot write down this term. Complex root can be only, complex roots are always conjugate. Okay. So if I write down s square is equal to plus minus j1, s equal to s1 s2 is equal to plus minus j1. That means s plus j1 equal to 0, s minus j1 is equal to 0. Then the factors will be s plus j1 s minus j1. Let us evolve this vector s square minus j1s. Okay. Then again, sorry, plus j1s. Then minus j1s. Okay. Then again minus j square 1. So I say s square, this j1s minus j1 gets cancelled. Minus of minus j square is minus 1, that into 1 s square plus s square plus 1. So my transfer function will become 1 upon s square plus 1 upon s square plus 1. So factors of the numerator, what will be factors of the numerator? Numerator is equal to 1. Okay, numerator is equal to 1, denominator is equal to s square term is 1, s term is 0, constant term is 1. So let us modify the program. Denominator is 101. Save this. Okay, save this. How many roots are there? Now there are only two roots. So I will say there are only two roots. Okay, s1 and s2. There are only two, not three roots. Let us save this and then run this. So you can see that all the imaginary real part is 0. So system is marginally stable. Let us see what will be the polar diagram, impulse response. See here, this impulse response is now oscillatory. This impulse response is now oscillatory response. So in this way you can play with the stability analysis. Okay, so Okay, so let us check with another program. Okay, let us check with another program. Okay, so this is the program. Okay, so let us do one hands-on program. Okay, before that we'll go to our presentation. Stability program. Okay, so let us say our system is 1 upon s plus 1, s plus 2, s plus 3. So what is numerator? 1. Denominator What will be denominator? S square plus 3s plus 2 into s plus 3. This is s square s cube plus 3s square plus 2s plus 3s square plus 9s plus 6. So this is s cube plus 6s square plus 11s plus. So denominator polynomial is 8, 6, 11. 8, 6, 11. Okay, let us come to hands on. Okay, clear or clear on CLC numerator is equal to 1, denominator is equal to, let us see what are the values of denominator. 8, 6, 11, 6. 8, 6, 11, 6. Let us see, let us define. Let us define now. This one is equal to transfer function of numerator comma denominator. Okay, numerator comma denominator. So this is the transfer function. Okay, then we care to find out poles zeros, poles and zeros. So poles G, not G, let's say this one, this one. Zeros, this one. Let us save this PZ1. Okay, hit the enter button. Zero is 0 into 1 empty, because this is a constant function, so no. If I say s plus 1, okay, let us modify my system as gs is equal to s plus 1 upon, sorry, s plus 4 upon s plus 1, s plus 2, s plus, then numerator will be equal to 1 4, denominator is equal to 8 6 11. Finish. Okay, let us see. If I write down 1 4, save it, and then hit enter. Okay, poles is equal to, okay, zeros is equal to zeros. S equal to minus, S equal to minus. Okay. You can plot pole zero diagram, PZ map, numerator common denominator, save this, and then run. Tell me, is this stable? From pole zero diagram you can easily get minus, this is add, this is 0, and these are poles. So all poles are lying on the left hand side of S plane, therefore system is stable. System is stable. Okay, in this way you can find out uh, value of system. Okay, so value of system. Okay, so just a minute. Okay, so this is pole zero diagram, or rather assessment of stability. Okay. Let us write one code. Let us write one code. So this is DC gain is equal to 5. Okay. Critical time is equal to 10. Okay. Input is equal to 2. Okay. Then we'll say S equal to transfer function S. Okay. Then I will say G equal to K underscore DC. K underscore DC. Okay. Slash TS plus 1. TCS plus 1. TC into S plus 1. Right. Then I will say TC into S plus 1. Okay. Then I will say step function U star G. Let us say what will be the value. We are calculating step response. Different so you can see step response. You can see the transfer function. DC value is 5 upon 10s plus 1. Okay, see the program. TCS plus 1. Okay, so in this way you can find out response. You can find out response. Okay, so let us see one fundamentals of this. Okay, so generalized system gain is equal to G is equal to K omega n square divided by S square plus 2 zeta omega n s plus omega n square. This is generalized form of which system? Second order system, where K is DC gain, omega n is natural frequency of oscillation, zeta is equal to damping ratio. Damping, okay. Zeta is equal to damping ratio. Okay. So I will modify the program. Okay. Here I will write down omega underscore or rather Wn omega n is equal to 10. Okay, zeta is equal to 0.2. Okay, then s is equals to transfer function s. Okay, this is kdc into omega n cap 2. Okay, slash ADC is equals to S n S raised to 2 S square plus 2 into zeta into omega n into S, omega n into S plus omega n cap 2. Okay, this is ADC. Now we'll write down PZ map is equal to G. Sorry, PZ map G. We can define the axis range by typing x minimum minus 3 suppose plus 1 x maximum, then minus 15 is y minimum, then 15 is y maximum. 15 is y maximum, bracket closed. Okay, if you save this and run the program, okay, there is one more parenthesis we have missed. So if you run the program, this is continuous time system. Okay, see the pole 0 plot. See the pole 0 plot. What is GS? Okay, this is GS plot. How many second order system? Therefore, there will be 2 poles. Okay, let us see that. Let us see that if I put axis, okay, 0 3 0 2 0 3 0 2 or x min y min, sorry, x min x max, y min y max. Let us see. The figure. Let us run this once again. Okay, this is axis G. Let us write one command we missed, that is step. Save this, run this. figure 1, let us say figure 2. Save this. Okay, let us not define the axis for this. Let us say it will be open-ended. Okay, so this is figure 1. Pole 0 plot. System is clearly unstable. Let us define some axis. 0 to 15 and 0 to 50. Save this. Again run this one. Okay, you can modify the axis also. Let us keep it as 10. Let us keep this as 10. Run this. System is clearly stable because D's are on the left hand side of the S plane. Now let us play with it. Let us play with it. Okay, damping ratio, let us say this is minus. Let us say this is also minus. Then save this. Okay, so this is one of the thing. Now we will see the plot where what we will do is Okay, now let us see that. Okay, let us define one unstable system. Let us open a new script file, clear all, CLC. So let us define numerator is equal to 1 space 5. Okay, 1 space 5. Let us see denominator is equal to, let us define the system first of all, then we will write down the denominator coefficient. Okay, for unstability, system must lie on system roots must system root must lie on right half of S plane. That means real part of roots must be positive. So if I say the function s plus 5, s minus 3, s minus 4, then this is an unstable system. Let us do it. So s minus 3, s plus 4, s minus 4. Let us see denominator. So this is s square minus 7s minus 3s, yes, plus 12. So denominator coefficient will be equal to 1 minus 7, 12. Let us see, let us put this 1 minus 7, 12. This is denominator. Okay. Then what I will do is, okay, I will write down same code here. Okay, roots denominator s1 is real r1. Okay, then we will see whether system is stable or not. First of all, we will define this as numerator, this as denominator. Let us save this as unstable 1. Save it, then we will run this. System is unstable. Okay, let us see the figure. This is, there are two values, s equal to plus 3, s equal to plus 4, two poles. Okay, let us define pole 0 map for this, pz map. Okay, so it is already defined. let us say step response numerator comma denominator. Save. Let us see whether it is correct. Step response we must get. See the step response how it is. It is rising. It is rising. It is not going to zero. That means it is going towards instability. It is going towards instability. So we will define axis 0 20 0 20 axis. Okay, closed. Save and then again run it. Save this. Again run this program. So this is like this. Okay. Okay. System is unstable. So in this way you can find out system parameters. Okay, in unstable system also you can find out the parameters. Okay, you can find out the parameter. Okay, this is how you calculate step response. So we'll see something about growth array. Okay. 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 So one more program we'll write down. So system is stable. Okay. So let us see one more example. Okay. Okay. Here I will write down one new program. One new program. Suppose I write down numerator is equal to 1, denominator equals to 1 comma 2 comma 3. Okay. Then sys 1 equal to transfer function numerator comma denominator. Okay, this is transfer function. Okay, then I will say let us check this first. Okay, this is simple example 1. Let us check this first. Okay, then I will say zpk numerator comma denominator. Let us check. Okay, let us check. Okay, So this is pole zero gain model. Pole zero gain model. Okay. So in this way you can define. Now I will say that I will declare since G is equal to S plus 4 slash S plus 1 into S plus 2. Okay, then I will say ZPK is equal to G. Let us save this. Okay, so if I say sys1 G, okay, so in this way let us move on to another 1 comma 4, another form. So you cannot write down directly your transfer function. You have to write down in numerator coefficient and denominator coefficient. Okay, s square my plus 1 s plus 1 s plus 2 means s square plus 3s plus 2, s square plus 3s plus 2. Okay, this one numerator comma denominator. Okay, so save it, run this one. Equal to, we forgotten to write transfer function. This is equal to transfer function. Okay, we will write down ZPK sys1. Okay, save this, run this. So you will get zero pole gain model, zero pole gain model. Okay, Okay, in this way you can find out different transfer function. Okay, so today we'll close our discussion here only. Okay, so thanks a lot. Okay, thank you very much. Thanks a lot. And this is just before closing out how to get the Unacademy free plan running for you. Download app, install it, go to daily interactive live classes, GATE and ESE, plus subscription, check on it. You'll get many courses which are available for free. Okay. Okay. Step 6 will involve clicking on the video, then you will be invited to put in the invite code. Okay, if you put in my invite code SSM10, free plan will be unlocked. Okay, and then step paid, you will be able to use the program freely. Okay, the video course freely. Okay, or for free. So like us, subscribe us, comment on our channel. Okay, hit the bell icon for further notification. Use my code for some discounts, 10% discount, some registration and offers. Okay, also join our Telegram channel where we provide updates on upcoming videos. So thank you very much. Thanks a lot. And this is Sunil Manjani signing off for today. Thank you.